Okay, hi everyone. My name is Adrian Rehm. I'm a PhD student at Laurentian University, and I've been working on this for about 3 years, this project. And today I'm going to present research pertaining to basically my second research paper, research study, which really looks at the fluid generation in the Quetico and testing whether we're dealing with metamorphic origin for gold in those areas. And so this is a co-research with Laval University, of course, and Laurentian University and the Hartwell School of Earth Science. So we've heard a lot about the metamorphic devolatilization model up to this point, so I'm not going to go into it in any more detail. Really, my study is focusing on 3 and maybe 4 aspects of this model. And really what we're dealing with here is the fluids, looking at the molecular composition of the fluids that could be being produced during the prograde metamorphism. So what we're really interested in is the hydrogen being released from, basically continuously released along the prograde path from the breakdown of chlorites, other phyllosilicates, etc. And then the sulfur is going to be quite important here. There's kind of 2 reasons for this. The first is that a lot of people believe that we need to have sulfur in the fluid to bind as an HS aqueous species with gold to liberate it. And also the sulfur releasing reactions has to do with the breakdown of the sulfide phases, which, as Diogo demonstrated, is where we have the gold hosted. And then the third component is the carbon. We haven't talked a lot about that yet, but this is thought to be an important reaction or an important component of these fluids. We know that quartz carbonates are the most common vein types in these orogenic style settings. And this is basically because the carbon actually helps keep the fluid, keeps it buffered at a neutral composition or neutral pH, which is kind of needed for the HS species of gold. And the other component I'm going to talk about is deformation. It might seem obvious that, we need deformation to localize the fluids, but the timing of this is quite important because you need more than probably need more than just simple burial in order to get these fluids mobilized. You need probably the development of major regional and subvertical structures. Okay, so really 2 main objectives that with this study is really nailing the pressure temperature deformation evolution, kind of what Isaac was just describing with the Pontiac, because really we're lacking a robust estimate of the PT evolution for most of the basins in the Spear province. And so with that, we're doing a lot of work with isograds, looking at the if there is spatial variability of the pressure temperature conditions, and of course the pseudo-section thermometry. And then the second part of this is really to test this devolatilization model using the composition of the fluids. So here I've put the timing of prograde reactions. Really, I'm not going to touch on that for this talk, but we're really looking at what are the predicted compositions and the pulses of the fluids. When does that occur in the PT space? So the Quetico subprovince is one of the largest sedimentary basins in the world. In fact, it's about 1,200 kilometers along its long axis. The average is about 100 kilometers along its short axis, and it's estimated that the current depth of it is about 6 to 8 kilometers deep as its current exposure. So we can expect that it was a lot deeper in the Archean. So really a substantial basin. And what it makes it kind of interesting and important is that unlike some of the other places in the Superior, we have a full access to the northern and southern boundaries. It hasn't been truncated by the Grenville or whatever. So we can do full transects right through the low-grade part in the south to the high and medium to high grades in the middle, which is this darker gray unit. These are granulites. And into the low grade again in the northern part. The other interesting part of the Quetico is that we have variable endowment along its margins, as Diogo pointed out. Kind of probably the most important one is going to be the hard rock deposit, or that greenstone mine now. That's I believe it's about 4 million ounce or more at this point, gold deposit. And there's of course other deposits along in the Beardmore Geraldton area, similar tonnage. And then once we get into the Thunder Bay and Atikokan areas, we're really looking at only prospects and occurrences. So there's some variable endowment there. I just want to point out that this is a compilation map that I'm working on, and I've finished for the Quetico subprovince and its boundary areas. And so we've kind of compiled geochron data and historical maps to try and produce a stratigraphic assemblage map that's consistent across the boundary areas and the full Quetico map. I'm not going to talk about the stratigraphy too much in this talk, but I just wanted to mention that this is something that I am doing. Okay, so for the methods, the first part of it is going to be the field work and the GIS compilation that I was talking about. So I compiled lots of historical maps for the Quetico, all the whole rock geochemical data that's available, mostly from the OGS, and of course the uranium-lead geochronology from the OGS and other studies. Then the transect style mapping was done over 2 summers. We did about 15 transects and 600 outcrops that tried to cross different parts of the Quetico. And then we kind of bring it down to the micro scale, where we look at mineral assemblages and textures for all of our samples using optical microscopy, and some help with the micro XRF as well. We did SEM EDS for target samples that we want to do thermobarometry on, and then the probe chemistry for garnet and other phases, biotite, plagioclase, etc. For the whole rock chemistry, I carried out multivariate analysis, so centered log ratio, transformation, and then principal component analysis to look at the major elements and the trace elements. I'll talk about that a little bit. This was acquired by different ICP methods. And then the other part of it is the hydrogen, carbon, and sulfur volatiles, which was acquired using the complete characterization package with Metal Earth, and that is done with combustion furnace and infrared spectrometry. And then we have the phase equilibrium modeling, which is kind of the bulk of the technical stuff, where we use this program called Theriac Domino, which is a Gibbs free energy minimizer. This kind of gives you a sense of what the program is, and it's just a bit of a code. And we use this to do thermobarometry, determine what's the evolution again, and then kind of the next step is to look at the fluid, where we're not in an isochemical system. Now we're removing some of the compositions and seeing how the fluid evolves. Okay, so the Quetico is mostly characterized by these very thick sequences of turbiditic rocks with mostly laminated beddings, graded bedding, and rare cross bedding. And this again goes from phyllitic at the margins to gneissic and migmatitic in the core. The other units that are kind of important are the mafic volcanic units. These are pillowed flows, potentially sills, that are concordant and interlayered with the turbidites. This is an example of a contact there at the southern margin of the Quetico. And really, at the southern margin especially, there's a lack of major structures or an increase in strain at those margins. And from the maps, we can see that there's a huge amount of plutonism that's within the Quetico, and it's just a diverse suite of rocks. For the structural geology, I'm not going to go into too much detail on this. I think the main points here is that we have almost all the structures are subvertical to steeply dipping. Horizontal or even 40-degree dipping structures are incredibly rare in the Quetico. The main foliation is actually in most places a composite foliation between the subvertical D1 structures and subvertical D2 structures. Only in a few places, such as the photo on the bottom there, do we see any relationship between the two. And so this D2 structure has a very variable plunge. Usually the difference is as we go from the margins into the center, it appears to get shallower, the plunge. And then D3 is the common late dextral overprint that we see in most of these greenstone belts. For the regional metamorphism, we've looked at 7 or 8 metamorphic zones, starting at the chlorite sericite, right in the margins, or right at the margins and within the volcanic zones. And then we go through biotite, garnet, and then storolite, andalusite, coming in about the same time. So we usually see that association of the two minerals, which is interesting. Cordierite is shortly after, cordierite and sillimanite. And then in the center, we're getting migmatites and locally orthopyroxene. Not shown on this map, but most of the orthopyroxene is going to be actually to the east in the Manitouwadge area. One of the important observations is that the sequence of isograds is mirrored on both sides of the subprovince. The isograds are discordant to the main bedding and major composite foliation. And a lot of the times they actually pass over major subprovince bounding faults. Occasionally they are displaced by these faults, but for the most part they are overprinting them. So petrography was first used to just come up with groups of different rock types for the metasediments that display similar mineral assemblages. So we have kind of 3 main rock types, which is the peelite, which just characterizes rocks that have aluminosilicates and storolite, cordierite at medium grades. The semi-peelite is more quartz-rich and rarely contains any of those minerals. And then the calc semi-peelite is similar to the semi-peelite, but now we have amphibole and epidote and calcite a lot of the times. So this is kind of how I've classified them, just based optically as a first pass as to how to differentiate these different units. And then, so once I have a sense of what the different units are based on petrology, we used PCA analysis for the major and trace elements to see if we can group these different rock types based on their chemistry, and we were successful in doing that. We also applied that to historical data too. And so the main differences are going to be from the covariance of silica and ferromagnesian minerals. So that's just really differentiating the mafic sediments versus this big block of intermediate sediments. The main difference between the peelite, semi-peelite, and calc semi-peelite is going to be the opposing covariance of potassium and iron, and calcium and sodium. So really this represents differences in the clay and plagioclase quartz content of the rock. And it's probably attributable to hydraulic sorting of the clays. Most of the rocks contain pretty pristine plagioclase, so it's probably not much of a weathering effect, at least for the coarse grain samples. And then we applied random forest classification on the full data set using the training samples in the petrography to give us a sense of what's the average composition of the Quetico sediments. So here it's mostly semi-peelite, 45%, quite a bit of calc semi-peelite, 22, and then only 30% are actually peelites. So most of the rocks in the Quetico do not contain porphyroblasts, which is an important factor here. Okay, moving on to the volatiles here. What this diagram is showing is the relative distance of the samples from the inferred isograd. So I've just measured the distance on the map using ArcGIS, and then applied the volatile content to see their distribution. For water, we see basically a continuous decrease along throughout the whole sequence of isograds. I would say the most prominent decreases occur at this just after the biotite isograd. There's a drop in about 8 or 10 to 6 mole percent water, and then there's another big drop once we get into the OPX zone. Of course, that's when biotite is breaking down to form OPX. The carbon is actually quite significant. There's a large drop at about the same time at this biotite, near the biotite isograd. And then for the sulfur, really there's not a visible trend there, as you can see. Maybe a slight decrease if you squint. But so what do we know about the textures that are telling us these trends? We have calcite in the chlorite and biotite zones. These are often quite big, rounded calcite grains. They're evenly distributed in the whole matrix. They don't form, and a lot of times they don't form connective films, which you'd expect for veins. They show evidence of triple junctions, so potentially dynamic recrystallization, and the inclusions trails seem to be continuous through these grains. So it would indicate to me that we're dealing with porphyroblasts as opposed to veins. So this is important because then we're probably dealing with some sort of primary calcite, or early calcite at least. Once we get into the garnet zone and plus, then we're not seeing any of these carbon-bearing phases. No graphite, no carbonate, nothing. For the sulfides, Diogo talked about those textures quite a bit, so I'm not going to reiterate that. But here we see that the pyrrhotite to pyrite content is quite variable throughout the Quetico, and usually you have a mixture of both. Pyrrhotite only is often in the higher grade zones. So now, looking closely at the thermometry, we used primarily garnet zoning as kind of a way to target the PT conditions that the garnet experienced while it grew. I think the most important here is that we have kind of a gradual increase in the iron and iron and magnesium content as we go from the core to rims, which is just what we'd expect for a pro-grade garnet. The grossular content is mostly flat until we get to the margins where there appears to be a sharp decrease. So looking at, now putting this on a pseudo section, I'll just kind of explain this diagram because it's a bit messy, but this is the field of the observed assemblage in gray. So there's a pseudo section, and I've just taken off all the other lines just to show the ones that are defining the mineral assemblage. The light gray is the mode of garnet. So we increase the garnet, we grow garnet as we increase temperature. And then these other colored lines are the actual contours of the garnet chemistry, as well as there's biotite chemistry and plagioclase. So the closest intersection of the compositional isoplex occurs at about 7 kilobars and 560 degrees Celsius. And so using the zoning profiles that I just showed, we can infer that this is kind of a normal increasing PT gradient. And then you get perhaps a sharp decrease at the very end of garnet growth, as characterized by that really sharp grossular rim. Now looking at some higher grade samples, the almandine is similar, but now we have the opposite zoning in pyrope. So we're dealing with a different path now. And so what we've inferred here is that we're actually decreasing pressure along this garnet mode, and then the garnet, you actually produce a little bit of garnet once you pass the cordierite in isograd, or the cordierite in line, and we actually get into the Andalusite field. So compared to the Pontiac, we're probably getting to much lower pressures, about 3.5 kilobars. So now using the gradients that we just discussed, mostly just the garnet zone gradient, because this is where we're getting the most fluid production. At the start, we have a semi-peelite, or maybe even calc semi-peelite in the chloride zone, which has calcite, white mica, and chlorite, K-feldspar, and pyrite and pyrrhotite. So this is predicted and observed in the assemblage. So at this point, at 400 degrees C, the fluid is almost entirely water, very little CO2 and very, very little hydrogen sulfide in the fluid. Moving along to 450 degrees C, we get a high fluid production by the breakdown of K-feldspar to form biotite. Again, the composition is still quite hydrogen rich, a little bit more carbon at this point, and the sulfur is still quite low. And then really the main fluid production occurs at about 505 kilobar or degrees C. At this point, we have a huge increase in the carbon content because calcite is now totally reacted out. So again, this should probably be considered an upper limit for XCO2 because we are getting fluids that are coming probably from depth that will be diluting that. But really, this is characterized by the reaction of white mica plus chlorite to form biotite, maybe a little bit of garnet at that stage. So for a summary, we have that the isograds are continuous along the long axis for several kilometers, hundreds of kilometers, and it's mirrored on both sides of the margins. So we have a similar tectonic evolution on both sides. The PT path follows a relatively high pressure temperature gradient, probably a burial, followed by a really sharp and significant isothermal decompression at the storolite cordierite boundary. So that's probably where we're actually bringing up the core of the Quetico. The peak fluid release again appears to have occurred at least for semi-peolites at the biotite near the biotite in reaction. We see that in the predictions and the modeling. We see that in the volatile chemistry. And then, of course, we have a lot of CO2 at the same time, which is probably important for keeping the neutral pH. The sulfide phases partially break down along that PT path, but only a very small amount of sulfur goes into the fluid. So potentially there's enough sulfur there to mobilize gold, but probably not enough sulfur to bring any pyrite with it. So that's all I have. Thank you.